Learning objectives. In this chapter, the user would learn the following aspects of analysis of algorithms, algorithm and programs, efficiency of algorithms, big O notation, comparison of algorithm, sorting algorithm. The history of big O notation. The big O notation has been used in mathematics for more than a century. In computer science, it is widely used in the analysis of algorithms. The German mathematician Paul Bachmann first introduced a big O notation in 1892 in an important book on number theory. The big O symbol is sometimes called a Landau symbol after the German mathematician Edmund Landau, who used this notation throughout his work. The history of big O notation. The use of big O notation in computer science was popularized by Donald Knuth, who was also introduced by the big O, and big O notations defined later in the section. Working with the definition of big O notation, a useful approach for finding a pair of witness is to first select a value of k for which the size of modulus of f of k can be readily estimated when x greater than k, and to see whether we can use this estimate to find a value of c for which modulus of f of x less than or equal to c into modulus of g of x for x greater than k. Big O estimates for some important functions. Polynomials can often be used to estimate the growth of functions. Instead of analyzing the growth of polynomials each time they occur, we would like a result that can always be used to estimate the growth of a polynomial. Theorem 1 does this. It shows that the leading term of a polynomial dominates its growth by asserting that a polynomial of degree n or less is order of x of n, that is called O of x of n. Let f of x equal to an into xn plus an minus 1 into xn minus 1 plus etc. plus a1 into x plus a naught, where a naught, a1, etc. an minus 1, an are real numbers, then f of x is order of xn, that is called O of xn. Proof. Use the triangle inequality. If x greater than 1, we have if modulus of f of x equal to modulus of an into xn plus an minus 1 into xn minus 1 plus etc. plus a1 into x plus a naught less than or equal to modulus of an into xn plus modulus of an minus 1 into xn minus 1 plus etc. plus modulus of a1 into x plus modulus of a naught equal to xn into order of modulus of an plus modulus of an minus 1 by x plus etc. plus modulus of a1 by xn minus 1 plus modulus of a naught by xn order of less than or equal to xn into modulus of an plus modulus of an minus 1 plus etc. modulus of a1 plus modulus of a naught. This shows that if modulus of f of x less than or equal to c into xn, that is called cxn, where c equal to modulus of an plus modulus of an minus 1 plus etc. plus modulus of a naught, where x greater than 1. Hence, the witness c equal to modulus of an plus modulus of an minus 1 plus etc. modulus of a naught and k equal to 1 show that f of x is order of xn. We now give some examples involving functions that have the set of positive integers as the domains. How can big O notation be used to estimate the sum of first n positive integers? Solution. Because each of the integers in the sum of the first n positive integers does not exceed n, it follows that 1 plus 2 plus etc. plus n less than or equal to n plus etc. plus n equal to n2. From this inequality, it follows that 1 plus 2 plus 3 etc. plus n is order of n2. C equal to 1 and k equal to 1 as witness. In this example, the domains of the functions in the big O relationship are the set of positive integers Big O estimates will be developed for the factorial function and its logarithm. These estimates will be important in the analysis of the number of steps used in sorting procedures. Properties of Big O notation. If f is order of g and g is order of f, then one says that f and g are of the same order if f is order of g and h of x into g of x for all positive real numbers x, then f is order of h. Then O notation describes upper bounds on how fast functions grow. Example, f of x equal to x square plus 3x is order of x2, but also order of x3, etc. Often one looks for a simple function g that is as small as possible such that still f is order of g. The word simple is important since trivially f is order of f. Useful, Big O estimates if d greater than c greater than 1, then nc is order of nd, but nd is not order of nc if b greater than 1 and c and d are positive, then log bn c is order of nd, but nd is not order of, then log b into n whole bracket into c is order of nd, but nd is not order of log b into n whole bracket into c. If b greater than 1 and d is positive, then nd is order of bn, but bn is not order of nd. If c greater than b greater than 1, then bn is order of cn, but cn is not order of bn. If f1 of x is order of g1 of x and f2 of x is order of g2 of x, then f1 plus f2 into x is order of maximum of j g1 of x into j g2 of x into j. We have to see the maximum between these two values. If f1 is order of g1 and f2 is order of g2, then f1 plus f2 is order of g1 plus g2. Note, these estimates are very important for analyzing algorithms. Suppose that g of n equal to 5n2 plus 7n3 and f is very complex function that you cannot determine exactly, but you know that f is order of n3, then you can still derive that n into f of n is order of n4 and g of f of n is order of n6. Big omega notation. Definition. Let f, g or factorial into r, we say that f is order of g if there are constants c and k such that 8x greater than k, f is big omega of g. The constants c and k are called witness to the relationship between f and g. Big O gives an upper bound on the growth of a function, while big omega gives a lower bound. Big omega tells us that a function grows at least as fast as another. Similar abuse of notation as for big O. F is order of g if and only if g is order of f. Prove this by using the definitions of O, that is called order, and dot. Big theta notation. Definition. Let f, g or factorial into r, we say that f is order of g if there are constants c and k such that 8x greater than k. We say that f is big theta of g and also that f is order of g and also that f and g are of the same order. F is order of g if and only if there exist constants c1, c2 and k such that c1 into g of x less than f of x less than c2 into g of x if x greater than k. This follows from the definitions of big O and big omega. Sorting algorithm. Ordered linear search, junk search and binary search each assume that the underlying array or list which is being searched is already in sorted order. How can one take an unordered array or list or sort it? Algorithms for sorting are fundamental to computer science and dozens have been developed. In this section, we shall consider three such algorithms: insertion sort, selection sort, merge sort. Insertion sort. Insertion sort corresponds to the method that many people use to sort cards as they are being dealt to them. The first card is placed in one's hand. The second card is compared to the first and placed either before or after it, and so on. In general, one has some I cards in sorted order in one's hand, and the I plus first card is compared to successive cards starting from the left or right until the proper location to bar insert the card is found. Let us consider how to sort this array using insertion sort. Imagine the numbers 34, 16, 12, etc. being bar dealt to you. In this order, like cards, you would start with the number 34, a trivially sorted list. Then the number 16 would be inserted into this list, producing the sorted list bar 16, 34. The number 12 would then be inserted into this list, producing bar 12, 16, 34, and so on. In general, in phase K of the algorithm, the kth element of the array is inserted into the sorted list formed from the first k-1 elements of the array. The process of insertion sort is shown below, where a diamond tree is used to separate the processed and sorted array elements from the as yet unprocessed array elements. Analysis. What is the running time of insertion sort on an array containing n elements? In phase 1 of the algorithm, the first array elements must be examined. In phase 2 of the algorithm, the second element must be examined and compared to the first, which must therefore be examined. In general, in the kth phase of the insertion sort, the kth element must be examined, and in the worst case, it may be compared to each of the previously k1 elements, resulting in k total elements being examined. Thus, the total number of elements examined in the worst case is given by 1 plus 2 plus 3 plus etc. plus n minus 2 plus n minus 1 plus n. Selection sort. While insertion sort can be used to process cards on line as they are being dealt, the next algorithm we shall consider cannot proceed until all the cards have been dealt. However, in sorting a list or array of elements that are all given in advance, both algorithms are equally applicable. Selection sort begins by examining the list of elements, bar selecting the smallest one and bar swapping it with the first element of the list. In phase 2, selection sort selects the smallest element from the remaining n-1 elements and swaps it with the elements in position 2. In general, in the kth phase, selection sort selects smallest element from the remaining n-k+1 elements and swaps it with element in position k. Analysis. What is the running time of selection sort on an array containing n elements? In phase 1 of the algorithm, all n elements must be examined in order to end of the smallest element. In phase 2 of the algorithm, then n-1 remaining elements must all be examined to find the second smallest element. In general, in phase K of the algorithm, the remaining n-k+1 elements must all be examined to determine the kth smallest element. Thus, the total number of elements examined is given by n plus n-1 plus n-2 plus etc. plus 3 plus 2 plus 1. Merge sort. We shall consider a third algorithm for sorting, merge sort, whose implementation is inherently recursive and whose analysis depends on the mathematical technique of recurrences. Merge sort is probably faster than either insertion sort or selection sort in the worst case. Comparison of algorithm. Unordered linear search. Suppose that the given array was not necessarily sorted. This might correspond, for example, to collection exams which have not yet been sorted alphabetically. If a student wanted to obtain her exam score, how could she do so? She would have to search through the entire collection of exams, one by one, until her exam was found. This corresponds to the unordered linear search algorithm. Note that in order to determine that an object does not exist in the collection, one needs to search through the entire collection. Unordered linear search. Consider executing the unordered linear search algorithm on this array while searching for the number 11. The first four elements would need to be examined until the fourth element containing the value 11 is found. In analyzing the performance of search algorithms, we will consider these examination counts as a measure of the performance of such algorithms. Now consider executing the unordered linear search on this array while searching for the number 13. Since 13 does not exist in the array, one must examine all 8 of the array elements until one could definitely return bar 13 not found. Ordered linear search. Now suppose that the given array is sorted. In this case, one need not necessarily search through the entire list to ND a particular object or determine that it does not exist in the collection. For example, if the collection of exams were sorted by name, one need not search beyond the bar piece to determine that the exam for bar Peterson does or does not exist in the collection. A simple modification of the above algorithm yields the ordered linear search algorithm. Note that while scanning the array from left to right, smallest to largest values, a search can now be terminated early if when it is determined that the number being sought and as yet not found is less than the element currently being examined. Ordered linear search. Consider executing ordered linear search on this array while searching for the number 11. In this case, the first two elements would need to be examined until the second element containing the value 11 is found. Now consider executing the ordered linear search on this array while searching for the number 13. Note that only the first four elements need be examined until the value 16 is encountered, and one can definitely return bar 13 not found. Chunk search. Given an ordered list, one need not, and one typically does not, search through the entire collection one by one. Consider searching for a name in a phone book or looking for a particular exam in a sorted pile. One might naturally grab 50 or more pages at a time from the phone book, or 10 or more exams at a time from the pile to quickly determine the 50-page or 10 exam bar chunk which the desired data lies. One could then carefully search through this chunk using an ordered linear search. Let C be the chunk size used. Example, 50 pages or 10 exams. We shall refer to the algorithm encoding the above ideas as chunk search. Consider executing the chunk search on the above array while searching for the number 34 and using C equal to 3, that is, chunks of size 3. To determine if 34 is in the first chunk, the third element at the end of the first bar chunk with value 12 must be examined. Since 34 greater than 12, we next examine the sixth element at the end of the second bar chunk with value 37. Since 34 less than 37, we conclude that the value 34, if it exists in the array, must be contained in the second chunk. We then simply execute ordered linear search on the subarray A of 4:6, consisting of the three elements in the second chunk, eventually ending 34 in the fifth position. Now consider executing chunk search on the above array while searching for the number 33. Chunk search would behave exactly as described above, except that the call to ordered linear search would return bar 33 not found when searching the subarray A of 4:6. Binary search. Now consider the following idea for a search algorithm using our phone book example. Select a page roughly in the middle of the phone book. If the name being sought is on this page, you are done. If the name being sought occurs alphabetically before this page, repeat the process on the bar first half of the phone book. Otherwise, repeat the process on the bar second half of the phone book. Note that in each iteration, the size of the remaining portion of the phone book to be searched is divided in half. The algorithm applying such a strategy is referred to as binary search. While this may not seem like the most bar natural algorithm for searching a phone book, consider executing the binary search on this array while searching for the number 34. To determine if 34 is in the first or second half of the array, we split the array in half, considering the fourth element at the end of the bar first half, whose value is 16. Since 34 greater than 16, we conclude that the number 34, if it exists in the array, must be contained in the second half, that is the sub-array A of 5:8. We then repeat on the second half of the array, splitting it in half and considering the sixth element whose value is 37. Since 34 less than 37, we continue with the sub-array A of 5:6, ending the element whose value is 34 in the next iteration. Now consider executing binary search on this array while searching for the number 33. Binary search will behave exactly as described above until the last subarray of size 1 containing only the element whose value is 34 is considered. At this point, one can definitely return bar 33 not found, since there are no subarrays yet to be searched which could possibly contain the number 34. Analysis of algorithms. Introduction. One of the major goals of computer science is to understand how to solve problems with computers. Developing a solution to some problem typically involves at least 4 steps: designing an algorithm or step-by-step procedure for solving the problem, analyzing the correctness and efficiency of the procedure, implementing the procedure in some programming language, and testing the implementation. The absolute execution time of an algorithm depends on many factors. The size of the input. Searching through a list of length 1000 takes longer than searching through a list of length 10. The algorithm used to solve the problem, unordered linear search, is inherently slower than binary search. The programming language used to implement the algorithm, interpreted languages such as BASIC, are typically slower than compiled languages such as C++. The quality of the actual implementation, good tight code, can be much faster than poor, sloppy code, and the machine on which the code is run, a supercomputer, is faster than a laptop. Algorithm and programs. Algorithms. In analyzing the efficiency of an algorithm, one typically focuses on the first two of these factors: speed of the algorithm as a function of the size of the input on which it is run. One typically determines the number of program steps or some count of other interesting computer operations as a function. Input time will depend on the programming language used, the quality of the code produced, and the machine on which the code is run. An algorithm is a finite sequence of precise instructions for performing a computation or for solving a problem. Set the temporary maximum equal to the first integer in the sequence. The temporary maximum will be the largest integer examined at any stage of the procedure. Compare the next integer in the sequence of the temporary maximum, and if it is larger than the temporary maximum, set the temporary maximum equal to this integer. Repeat the previous step if there are more integers in the sequence. Stop when there are no integers left in the sequence. The temporary maximum at this point is the largest integer in the sequence. Properties of algorithms. There are several properties that algorithms generally share. They are useful to keep in mind when algorithms are described. These properties are: input. An algorithm has input values from a specified set. Output. From each set of input values, an algorithm produces output values from a specified set. The output values are the solution to the problem. Definiteness. The steps of an algorithm must be defined Precisely. Correctness. An algorithm should produce the correct output values for each set of input values. Finiteness. An algorithm should produce the desired output after a finite but perhaps large number of steps for any input in the set. Linear search. Pros. Locate an item in a list of examining the sequence of list elements one at a time, starting at the beginning. More formal pros. Find item X in the list A1, A2, etc. An. First compare X with A1. If they are equal, return the position 1. If not, try A2. If X equal to A2, return the position 2. Keep going, and if no match is found, when the entire list is scanned, return 0. Binary search. Pros description. Assume the input is a list of items in increasing order and the target element to be found. The algorithm begins by comparing the target with the middle element. If the middle element is strictly lower than the target, then the search proceeds with the upper half of the list. Otherwise, the search proceeds with the lower half of the list, including the middle. Repeat this process until we have a list of size 1. If the target is equal to the single element in the list, then the position is returned. Otherwise, 0 is returned to indicate that the element was not found. Greedy algorithms. Optimization problems minimize or maximize some parameter over all possible inputs. Examples of optimization problems. Finding a route between two cities with the smallest total mileage. Determining how to encode messages using the fewest possible bits. Finding the fiber links between network codes using the least amount of fiber. Optimization problems can often be solved using a greedy algorithm which makes the best by a local criterion choice at each step. This does not necessarily produce an optimal solution to the overall problem, but in many instances it does. Efficiency of algorithms. Efficiency. Amount of resources used by an algorithm. Space, number of variables. Time, number of instructions. When designing an algorithm, must be aware of its use of resources. If there is a choice, pick the more efficient algorithm. Efficiency of algorithms. How to measure time efficiency? Running time. Let it run and see how long it takes. On what machine? On what inputs? Time efficiency depends on input. Example, the sequential search algorithm. In the best case, how fast can the algorithm halt? In the worst case, how fast can the algorithm halt? Time efficiency. We want a measure of time efficiency which is independent of machine, speed, etc. Look at an algorithm, pseudocode, and estimate its running time. Look at two algorithms, pseudocodes, and compare them. Time efficiency of an algorithm. The number of pseudocode instructions, steps executed. Is this accurate? Not all instructions take the same amount of time, but good approximation of running time in most cases. Time efficiency. Worst case efficiency is the maximum number of steps that an algorithm can take for any input data values. Best case efficiency is the minimum number of steps that an algorithm can take for any input data values. Average case efficiency. The efficiency averaged on all possible inputs must assume a distribution of the input. We normally assume uniform distribution, all keys are equally probable. If the input has size n, efficiency will be a function of n. Analysis of sequential search. Best case 1. Comparison. Target is found immediately. Worst case 3n plus 1. Comparisons. Target is not found. Average case 3n plus 1 by 2 plus 4. Comparisons. Target is found in the middle. Space efficiency. How much space is used in addition to the input? Efficiency of copy over. Best case. All values are 0. No copying. No extra space. Worst case. No 0 value. N elements copied. N extra space. Time n. Extra space n. efficiency of a shuffle left, space, no extra space except few variables, time, best case, no zero value, no copying, implies order of n equal to O of n, worst case, all zero values. Every element thus requires copying n minus 1 values 1 to the left, n into n minus 1 equal to n2 minus n equal to order of n2, that is called O of n2, y, average case. Of the values of 0, n by 2 into n minus 1 equal to n2 minus 1 by 2 equal to order of n2 equal to order of n2, that is called O of n2. Conclusion. In this chapter, the users have covered the following aspects of analysis of algorithms: algorithm and programs, efficiency of algorithms, big O notation, comparison of algorithm, sorting algorithm,